systems. Diesel particulates are typically soot particles with adherent hydrocarbons, sulfate and other condensed compounds. Soot particles are known as PM, or particulate matter. The collected particulate matter in a diesel particulate filter, if not removed, can create an obstruction to exhaust gas flow. The particulates are removed by a regeneration process which incinerates the particles. The DPF is located before or after the NOx catalyst. A major feature of the DPF is its ability for regeneration. Regeneration is very important since an overfilled DPF can damage or cause poor running of the engine due to excessive exhaust back pressure. The material trapped in the filter is in the most part carbon particles with some absorbed hydrocarbons. Regeneration is controlled by the temperature of the exhaust gases within the DPF. This can be done under normal driving as a spontaneous regeneration, in response to a warning light as in dynamic regeneration, or via a scan tool known as service regeneration. When the particulate loading of the DPF reaches a predetermined level, the DPF is actively regenerated by adjusting various engine control functions such as post-injection, intake air valve position, EGR and turbocharger boost pressure. The prime objective of these functions is to raise the exhaust gas temperature to a predetermined level. For more information on DPF operation and construction, please watch our training video on DPF fundamentals. The differential pressure sensor is used by the ECM to monitor the condition of the DPF. Two pipe connections on the sensor are connected to the inlet and outlet of the DPF. This allows the sensor to measure the inlet and outlet pressures. The pressure sensor contains a piezo-resistive element, signal amplification, conditioning and temperature compensation electronics. As the amount of particulate matter trapped by the DPF increases, the pressure at the inlet side of the DPF increases compared to the DPF outlet. The ECM may use this information to calculate the accumulated soot mass. By measuring the pressure difference between the DPF inlet and outlet and the DPF temperature, the ECM can determine if the DPF requires regeneration. The ECM may recognise if the DPF is overloaded, if the differential pressure under certain operating conditions exceeds the overload limit calculated by the ECM. Some vehicles use a DPF pressure sensor with only one exhaust connection. A comparison is made between this and atmospheric air pressure. Actual DPF soot content is calculated by the ECM using a time, distance and driving condition algorithm. The pressure sensor is monitored only to determine if a DPF regeneration was successful. If the DPF becomes blocked, the ECM will register a high pressure DTC and the malfunction indicator lamp will be illuminated. A blocked DPF may be caused by multiple failed regeneration events, mechanical or electrical failure of the EGR system, or failures in the fuel management system. The most efficient way to test the DPF system is by monitoring the DPF pressure sensor live data with a scan tool. With the engine idling, slowly increase the engine speed to around 2000 RPMs. There should be a pressure increase of around 20 kilopascals. Very little pressure increase would indicate exhaust gases flowing through the DPF uninterrupted. This may be caused by a damaged or collapsed DPF or damaged or disconnected pressure pipes from the sensor. An excessively high pressure value may indicate a blockage in either one of the sensor pipes, the sensor, or the DPF itself. Disconnect the sensor and turn the ignition on. Test for between 4.8 and 5.2 volts on the high reference terminal. This is done by connecting the meter between the terminal in the harness connector and battery negative. Check the ground circuit by connecting the meter between battery positive and the ground terminal in the pressure sensor harness connector. You should see battery voltage. The signal circuit on this system uses a pull-down monitored signal. To test this circuit quickly and accurately, I'll need to monitor the scan tool data while changing the signal voltage on the circuit. I'll use a fuse jumper between the 5-volt reference and the signal terminal. The scan tool pressure sensor data value should change from 0 to 5 volts. If there was any other value present, I would need to carry out further testing on that circuit. For a pull-up monitored circuit, I would need to watch the scan tool pressure sensor data change from 5 to 0 volts when jumped between the low reference terminal and the signal terminal. By performing this task, we've just confirmed that the sensor electrical circuit, including the ECM, are functioning normally. We can now perform a static test on the pressure sensor. Using a hand vacuum pump, apply vacuum to one side of the sensor while monitoring the scan tool data. The value should vary and transition smoothly without any spikes or dropouts. If the values were erratic, replace the exhaust differential pressure sensor. If the reading was okay, then the sensor is working correctly. If the value does not change, then inspect the sensor ports closely for any obstructions that may restrict gas flow. If the fault code suggested a DPF with an excessively high soot content or blockage, then you should only perform a forced regeneration once the ECM, electrical circuit, sensing pipes and sensor have been confirmed as serviceable. If the service regeneration proved ineffective, then the DPF can be removed for a closer inspection. If the DPF shows any sign of damage or deterioration, then it should be replaced. As technicians, we try to perform tests and checks in an order that's efficient and accurate. Consistent training is the key to effective diagnosis. Thanks for watching.